Students, we are getting ready for chapter one. Now, if you're reading ahead, wanting to get ahead, or just saying, hey, can I get a different perspective? I'm going to try to give that to you in these videos. There should be a video for each section as we go through the book. Completely up to you if you choose to follow along. But let's take a look, and I'll share my screen, and we'll open up with the first section. So I'm going to use this digital ebook. You have access to this. I think it's $10.99 a month, and the first 2 weeks are free or something like that. So you should be able to get out of this class for about 40 bucks, and next term, same thing. So depending on how you want to work it, you could choose to get the 13th edition of the textbook. Maybe you can find it for, I don't know, 50 bucks or something like that used. And if you can do that, hey, go for it, right? I mean, it's the 50 bucks instead of 80. But if you do try to find a new book, I'm pretty sure this book is pricey as a brand new book. But let's see here. Bilstein, Libeskind, Lot, 13th edition. Yeah, so Pearson, I feel like that might even be a rental cost. So used book 160. Let's see, what has Amazon got it for? Amazon's got it 146 used, brand new. I don't see a brand new one. Whew, duh, that's used. New and used from 135. So again, that's why look, you can pick the ebook option. You can access it anywhere. You don't have to carry the book around with you, or you could purchase the physical book. I'll leave that up to you. And again, this is not the only place you can buy the book. You can buy it other places, but we do need the 13th edition. The problems will line up with what is required for this course. All right, so let's take a look. Here we go. Introduction to problem solving. Now, this book is titled A Problem Solving Approach to Mathematics for Elementary School Teachers. So we're going to learn the concepts as we go through different chapters, and it's going to introduce things based on problem solving. So problem solving has a long history, and for a long time, people would solve problems in many different ways. And then one of the mathematicians in the 20th century, his name is George Polya. Polya came up and said, "Hey, let's take a look. Let me look at what problem solvers do. What do they do?" And they typically do four different steps. First step is understanding the problem. That's a big one. Second step is devising a plan. How am I going to attack this problem and then carry out the plan? And understand that you may have to use step four, which is looking back. You may have to go back a step and say, hey, that plan didn't work. So you may have to go back and devise a new plan and then continue. But what he also found is that the majority of great problem solvers spent the most of their time right up here in understanding the problem. So this is where I've seen college students, and they will very, very quickly glaze over a problem, reading very quickly, and they will miss out on some key terminology, or they'll solve a completely different problem. So I want to make you successful in this course, and that means making sure you understand that understanding the problem is the key. Now, this is from the Principles and Standards. This goes back to 2000. The National Council of Teachers of Mathematics had this: problem solving, reasoning, representation, connections, communication. These are mathematical processes. Problem solving is one of the 8 standards for mathematical practice in the Common Core State Standards. And we're going to integrate state standards, Common Core pieces throughout, because that's what you'll be teaching too. And just understand there are content standards, and then there are practice standards for mathematical practice. And we're going to be kind of integrating both of those as we go. Okay. So now I want to make sure it's very clear. There is a big difference between solving a problem and completing an exercise. So think of yourself at the gym, right? At the gym, if you go to the gym, you get on a bike. It's a stationary bike and you can pedal. Now, what you're doing is you're exercising your muscles. You're getting ready for really doing something. Now, when you get to the Tour de France, or you're riding your bike up a hill or a mountain, that's very, very different. And along the way, you may encounter different issues. So one of them is problem solving. The other one is exercise. And so we will assign some exercises, but they are not challenging in the same way. Problem solving requires a plan, and exercise may require you just to quickly, oh, I just need to do this, and then actually doing it. Like adding fractions, adding two fractions, for example, is typically not a problem solving component. Reading a description of a situation, having to figure out what are the fractions and then using them, that is problem solving. Okay. Now, Notice here at the bottom, I'm not going to read every page, but a reasonable amount of tension and discomfort improves problem-solving performance. What we call this in the biz is we call this the ability to have some frustration, but not enough to make you quit. And so that's what we want to do. It's okay to have this productive struggle as long as you are like still feeling, okay, I'm working towards the goal. That didn't work, but I'm going to try something else. If you get to a point where you're so frustrated that you want, I'm done with this problem. Feel free in the homework to move on to the next question. They typically are not linked in order, but put a little star by it. Leave some space in your work and then come back to it and see if you can't solve it later. Sometimes it just takes a stepping away from it. I'm going to click on the next page. Here we go. So these are the 8 standards of mathematical practice. This is going to be integrated throughout the entire course. These are things I expect all of you to have in your tool belt because you're going to be expected to teach it to kids. So we'll be utilizing these, construct viable arguments and critique the reasoning of others. Okay. Yes, you're going to be a teacher, right? You're going to have to critique other people's reasoning. And I usually include a few questions on the test where you have to do just that. A student says this, how do you respond? Okay. All right. Okay, now feel free to read through the text as you go, but that was the first little intro piece, and we'll get into section 1.1. Now, section 1.1 talks about mathematics and problem solving. And it gives you a pretty good idea, a much more in-depth component for the 4-step problem solving process that George Polya came up with. Okay. Now, understanding the problem is the key. If you listen to some of these on TikTok, YouTube Shorts, Instagram, they'll put these little problems out and they'll catch people on the street with the microphone. They'll be like, what about this? And then they answer quickly because they didn't think about it. They just heard something, they answer so quickly. And then you get to laugh at them because that's a fun thing, right? But what it does is it highlights that these folks are not taking time to understand the problem. Okay. So when you say, a shepherd has 36 sheep, all but 10 died. How many lived? Most of the time, if you catch someone on that, it's because they are it's thinking 36 sheep. Oh, died. Some of them died. And the word 10 died. So in your mind, if you're reading quickly, this is what tends to happen. I heard 36 sheep and I heard 10 died. Maybe I wasn't paying attention to what was being said. Maybe I wasn't even reading the problem fully. But that is a big problem. If you hear 36 sheep, 10 died, how many lived? You're going to answer 26, but it doesn't say that. What it does say is all of them but 10 died, right? Another way of phrasing that is, okay, 10 of them didn't die. So if you pause and think about it, you can get to the same place. And they say, how many of them lived? Hold on. All but 10 died. So 10 of them aren't dead. Oh, okay, 10. Now you're moving forward. Now you're to a place where you can start doing problem solving. You see what I'm saying? You can answer, you can do the subtraction quickly. That's not the issue. The issue is that you need to make sure you understand the problem. What are the unknowns? What am I supposed to find? What is needed? What information do I have? All of these are critical questions. Devising a plan. Now, we're going to see as we go through this course, not just here, but also in the first couple of days, we're going to be actually doing some of these plans in class. We're going to be looking for patterns. We're going to be making tables. We're going to be making a diagram. We're going to use guess and check. We'll work backwards, writing an equation. Nothing wrong with equations, right? Simpler problem, right? Solving a simpler problem, that is huge. Too often you see a case that says, find what happens in the 10th position, and you try to jump over, and all you know is the first, and you try to get to the 10th. Why? Pause for a second. What's the second position? Because maybe if you start thinking about what's in the second position and then the third position, you start seeing something and you go, oh, I can get there very quickly. But if you cut this out of the understanding of the devising of a plan, you try to jump to the end, I think you might struggle way more than you need to. So let's keep that in mind as we will move forward in this course. Once you've got a plan, go carry the plan out. Go do it. Say, okay, I think I'm going to use work backwards. Okay, now go do it and see what you end up with at the end. Make sure you keep an accurate record of your work. This is a big part of our class. You'll have many times a student say the answer is 12, and I will ask, how did you get that? And they'll say, I don't know, but I know it's 12. You see, that isn't great reasoning, and it's not going to help you if you're going to be a teacher of students. We've got to get to a place where we say, I'm not sure how I got there. I feel like the answer is 12. Now let me go through and think, how can I get there? How can I explain a process that gets me to this stage? You're going to be a teacher. This is not a class for someone who wants to go out and sit in a cubicle by themselves. This is for teachers. We have to work on our explanation and our own understanding. And when you get done with it, please look back. Please look back. It's so hard for me as a teacher, but I do get a lot of students who will answer a question like, how many miles away is this? And the answer they give is something like $10. And I'm like, what? In their mind, maybe in the service of the problem, it might have been like, oh, okay, yeah, we're talking about money. It costs this much to get from here to here. And they answer how much it cost, not how far. So I'm looking for miles, they answer in dollars. That's why looking back is important. Is my answer reasonable? Right? Did maybe sometimes if you're using the calculator, it's really easy to accidentally type the wrong thing in a calculator. I'm not lying. It can happen very quickly. So you have to check and see if your answer makes sense. Is it reasonable? If a hotel was $150 a night and you stayed 5 nights and the answer you get in your calculator is $50, we've got a problem, right? That does not make sense. Something went wrong. Go back and check. So let's keep that in mind as we work our way forward. Now, the rest of this indicates, and you're going to see these throughout, these are actual school textbook problems. This one's from grade 6, but here we go. John earns this much per week, helps for 3 weeks, tries to buy this. How much of his earnings does he have left? That is a problem. Sometimes you refer to these as word problems, but it gives you information. And to be honest, this is the only type of actual problem that we have. If I say, what is 15.5 times 3? That's not a problem. That's an exercise. Okay. All right, let's move on forward. Whew. Strategies. First strategy they use in this book is look for a pattern. Now, we are going to start off with a few definitions, and it's important, I think, as you go, definition-wise. So we have the natural numbers. The natural numbers are sometimes referred to with this symbol, or sometimes just a great, let me use a different thickness here. Sorry about that. Boop. Sometimes you might see the just as a great big capital N in bold, usually. But the one I showed you is the more mathematical notation of the natural numbers. So, or sometimes you'll see it like this, the natural numbers. Okay. But what does it mean? All that's great, but all it means is this is a set of numbers that starts with 1, goes to 2, goes to 3, and moves on. Also, these are sometimes referred to as the counting numbers because that's where students learn to count by going 1, then 2, then 3, then 4, and so on. Okay, so the counting numbers. And this story goes back a long time, but it was a fantastic, a fantastic situation, if you will. If you were this teacher, I could see it would have been really problematic. But a young student, his name was Carl Gauss. He Honestly, this is back in the time period. If you go back and look at when this occurred, it was way long ago, hundreds of years ago. And so, in order to do math, you had this piece, typically a piece of slate. You might remember those from chalkboards. And so, what you would do is you would write your answer down on this piece of slate. So, 34 plus 45, right? And then you'd put the answer. And then maybe you have a little bit of room down here, but most of the time you'd have to write the answer and then erase everything and put the number up on the top and then continue on with what you're doing. So Carl, as his friends call him, Carl, he was pretty chit-chatty, talkative, right? Always getting distracted, blah, blah, blah. And if you're a teacher or a parent, right, you're always trying to find something for the kids to do, right? Oh, I got to keep them busy. I got to keep them busy. What's going on? And so the teacher said, hey, Carl, look, I know the other students are doing addition and you're doing very well. That's great. But what I need you to do, could you just add up all the numbers from 1 to 100 for me? And with teachers probably laughing like, That's gonna take a while because it doesn't have much room on the board. And within a minute or two, Carl comes back up and goes, "Okay, yeah, I got it for you right here." And the teacher said, "No, no, no, no. I mean, add all of them up." And he's like, "Yeah, I did. I totally did." So let me share a whiteboard and we'll kind of see. Let's see how this works. Opening a whiteboard will stop screen sharing. Let's do it. Okay. Oh, give me a break. Okay, here we go. Let's see here. Whiteboard, new whiteboard, I guess. More work, less clicks. God, they update this all the time. All right, here we go. So here's what Carl did. Okay. So Carl's sitting there and he's like, hey, this is going to take a while. If I do 1 plus 2 plus 3 plus 4, maybe that's all that fits on that piece of slate. He's like, oh, then I got to add that up. Then I have to keep going. He said, wait a minute. Let me see if I can find a pattern. So Carl said, what if I do this? 1 plus 2 plus 3 plus, and put some dots and then just say all the way up to 99 plus 100. Writes that out. Okay. On the slate. Fits it in there. Right. And says, okay, I got that. Then underneath it says, why don't I write it backwards? So we're looking for a pattern. And so this would end with 2 and 1. And it's the same number of objects, right? 1 plus 2 plus 3 all the way up to 100. If you start at the 100 and work your way back, it's going to end with 1. And Carl said, I don't know what that is. Okay. And I don't know, it's going to be the same. Those are going to be the same when I add them together. So if I don't know what it is, maybe I can just call it something. I'm going to call it cloud for now. If you wanted to do something more algebraic, you could certainly write down something like the letter S to represent the sum of these. Okay. So he gets down, he says, okay, I end up with 2 clouds or 2 S's if you want more algebraic, again, depending on your background. Okay, so here we go. And then he noticed a pattern. Look at this beautiful pattern. 100 plus 1 is 101. 99 plus 2 is 101. 98 plus 3, 101. 99 plus 2, 101. 100 plus 1 is 101. That's not a coincidence. You see, every time, let me change color really quickly here. Every time that you move in the first pattern, you move up 1. In the second pattern, you move what? Down 1. If you look at the result of going up 1 and down 1, the total amount you have has to remain the same. So when you're looking at it, see this plus 1 and minus 1? Together, those are equal to 0. You're not making a change to the sum of the 2 terms. So Carl realized that and then said, hey, wait. Ooh, I like that, because Carl knew exactly how many numbers there were. 1, then 2, then 3, then all the way up to 100. That's 100 terms, 100 individual numbers. So he said, well, that means I must have 100 of these 101s, because that's what multiplication is, or at least it can be represented that way. But he said, but that's not my answer. My answer is not 100 times 101. My answer has to be half of that, because I have 2 of these. And then I think he probably used some of the nice pieces that you may remember, that these are commutative and associative, so I could regroup in any order. Maybe 100 divided by 2 would be better to do first, because that's just 50, and then multiply by 101. And if you want some fun facts, that's 50 times 100, which is 5,000, and 50 times 1, which is 50, and add those together. And that is the sum that Carl found, 50-50. And to me, that's pretty cool. Right? Look at that pattern. And that also means it didn't have to stop at 100. It could have gone as far as you wanted to. What if I want to find the sum of 1, 2, 3, 4, add them all up to 3,412? Oh, yeah, you can do that now. It also leads to the idea that maybe, just maybe, I could do something like this. What if I was adding 1 plus 3 plus 5 plus 7? Right? If I wrote that backwards, it'd be 7 plus 5 plus 3 plus 1. And each of these, when I add them, even though I went up 2, I also went down 2. So each of these is going to be 8. That's a beautiful pattern. And again, I don't know what that adds up to, but I know there's a bunch of 8s. In this case, there's 4 of them. And so maybe there's a way I can think of this sequence and figure out how can I figure out how many terms there are so that I can end down here with 4 times 8 and 2 times s. And that 2 times s gets cut in half, so s becomes 4 times 8 divided by 2. A little bit of work here. 2 times 8 gives me 16. I can get there. Now, yes, could you have come along here and said, but Scott, if I just take 7 plus 3, that's 10, and then I'll add 5 and 1, and that's 6, and I get 16 as well. Well, yes, there's many ways to solve a problem. There's many ways to find a sum. So what we're going to do is say we need to instead think about, is there a way that we could generalize? Could I get to a place where if I just found the 7 and the 3, that worked in that one case, the approach that Gauss was using would work all the time. All right. So let's jump back to the text. Ooh, what a fun one. Now, what you get to see at the bottom of the page is this is the authors letting you know that yeah, they just said you could generalize to anything. So what if they added up to a number n? So instead of going to 100, what if they went up to n? Maybe you could show why you might find a formula, not one that you have to memorize, because now you know where it came from. You don't have to memorize it. And that is a pretty cool idea. All right, let's jump ahead to the next page. Okay, next one says solve a related problem. What would you do if you saw 2 plus 4 plus 6 plus 8 all the way up to 100? How could you do it? Could you do it Gauss's way? Yeah. Could you do it visually? Maybe. If you say, wait a minute, 2 plus 100, that's 102. 4 plus 98, that's 102. Hey, I'm going to get a whole bunch of 102s. Bing, 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 bing. How many 102s would you get if you did it this way? Notice you didn't write it forwards and backwards. You don't have to cut it in half. What an amazing thing. Oh, it's amazing. This math stuff it's going to take you places, I'll tell you. So now you say, wait a minute, I have a whole bunch of these 102s. How many of them do I have? Well, I have 50 numbers here because we were going from 1 to 100, but now we're counting by twos. So it's going to be 50 numbers, but I'm pairing them up, which means I have 25 pairs. Done. 25 pairs. Every pair is 102, and I've got a way. Oops. Ooh, jump the gun a little bit there. And I've got a way to get the answer pretty quickly. All right. There we go. That's pretty cool. To me, it's pretty cool, but to you, it means you've got to be able to say, wait a minute, I need to practice some of these strategies because maybe I haven't done them in a while. So next couple strategies, I'll let you read through them in the textbook, but the idea is examine a simpler case and make a table. So what would I do to make a table? Notice this one says if 100 triangles are placed like this, 100 triangles, what is the perimeter of the figure that is formed? How interesting. What a great thought. I wonder how many that is. So if you're doing that, maybe you should, instead of jumping to 100 and trying to count how many there might be, you could say, wait, let me think. With one triangle, there's 3. With 2 triangles put together, there's 4. With 3, there's 5. With and every time I add a triangle, it goes up by 1. Interesting. So now I've got a really beautiful pattern that would allow me to say what should happen when I get to 100. What did I do? I examined a simpler case. I made a table to keep all of my work in line so I can understand what I'm doing. Bingo. Okay. They're going to work their way through a few other components. This one is a magic square problem. If you haven't seen them, they're kind of fun. You try to put numbers in so that every column and every row has to have the same sum. We actually call that a magic square. There's not actually anything magical about it, but in any case, that's the idea. Now, if you need all of these, so I need every row, column, and diagonal. So I need these 2, these 3, and these 3, right? I need them all to add up to the same number. Okay. Well, uh, uh, um, that's going to be a problem. Like you're going to be here for a while. That's what it feels like. If you try just guessing, yeah, you're going to be here for a while. But instead, you could say, wait a minute, if all three rows have to be the same, and I'm using the numbers 1 through 9, maybe I could just add up the numbers 1 through 9. And maybe I could even use, because that would be like adding all of the square up, right? So if I add all of the square up, I'll use Gauss's idea, right? I get 10, 10, 10, 10, and in the middle, as you might be able to say it here, I end up with just a lonely 5. So um, I could use Gauss's formula, which would tell me the number of numbers, which is 9, times the sum that I get if I write forwards and backwards. 9 plus 1 is 10. But remember, I'd have 2 of them if I use Gauss's technique. And so this becomes 9 times 5, which is 45. So what I know now is the sum of all the numbers is going to be 45, but I need 3 rows and they have to all be the same. So then you could say, well, wait a minute. I need each row to be 15. So then your plan now is not trying to pick all the numbers. You have a sub goal, a smaller task to do, which is how many ways can I get a sum of 15, right? Because I need a sum of 15. 1, 2, 3, 4, 5. I need it in a lot of different ways. Okay? So that becomes a sub goal, trying to write the sum of 15 in as many different ways as you possibly can. They make a chart. They start saying, wait a minute, how many different times does a certain number appear? And this is a great breakthrough because when they find all the different ways you can write 15, they start noticing that not every number shows up all as many times. Like the number 9. Number 9 shows up twice. Well, that's not very many times, right? The number 1 shows up twice. Hmm. Okay. I guess that's interesting. But it only shows up twice. If you remember that square, right? If I need something to add up twice and it has to be the same, I need it to be something like this. It has to be a number that's in one of these locations. And the reason why is if it was anywhere else, like let's just say I put the number 9 here, then it would have to appear in this, that diagonal, and the across. That's 3. It would have to appear 3 times. So that's not good. Okay. And if I was looking at what about the number in the middle? Well, the number in the middle has to be up and down, left and right, and then it has to be the 2 diagonals. So this number, whatever number it is, has to appear 4 times. So when you go over here and you start looking in your table, this is where things get fun. You're like, ooh, the number 5 shows up 1, 2, 3, 4 times. 4 times the number 5 shows up, and that is why the number 5 has to be in the middle. So you see what I'm saying? Problem solving. If you just start putting numbers in without thinking, without understanding the problem, without getting a plan, you could be there for a very long time and probably get very frustrated. My goal is to show you that it doesn't have to be like that, but you have to change the way you approach a problem. Okay. Next up is making a diagram, kind of drawing a picture. It helps sometimes to gauge, especially when you have different distances or different times. I'll let you read through that one. And the other one is work backwards. So working backwards is often what we use when we don't have algebraic skill yet. So you might remember questions like this. Um, Sally took half her money out of the bank on Monday. On Tuesday, she withdrew $3,000. On Wednesday, she withdrew half of the remaining money and she had $7,000 left. How much did she have on Monday? You could see this question in an algebra class. In an algebra class, the teacher would say, okay, here we go. Let's get this rolling. Actually, you know what I'm going to do? Give me a second here. I'm going to make some white space, right? There we go. That is beautiful. It's like I have my own whiteboard. Okay, so now let's take a look. Let's take a look. Okay, So if you were doing this algebraically, I know this one says work backwards. And the reason I want to do algebraically is I feel like some of you are going to be weak with algebra or feel less comfortable with it. So I'm going to push you a little bit at times to say, try it. So I don't know how much money Sally had, right? And I could call it anything I want. I could call it M for money. I could put a cloud because I don't know what it is. I'm giving you flexibility. So I'm going to use cloud because it's cool. So Sally had this much money. Then what did she do? Watch, just go through it in order. She withdrew half of her money. Ah, so how much does she have left? She has half left in the bank. Then on Tuesday, she took out $3,000, right? Then on Wednesday, she withdrew half of her remaining money. Well, this is the remaining money, and she took half of it out. And what remains was $7,000. So now I have this plan where I can go through and solve to get this. The reason why I wanted to set up algebraically is if you went backwards and said, okay, she had $7,000, then what? We know it says she withdrew half her money, but if you're working backwards, instead of taking half of her money, she puts in that amount of money, which means she should have $14,000, right? Because if she took out half going this direction, she'd end with seven. So we're not, we're going this direction. So she took out half, 14,000. Then she withdrew 3,000. Okay, so what's the going backwards of withdrawing your money? It's to put money in. Now she's at 17,000. And then it says she withdrew half her money. So at the end of the day, we get 34,000. Now, if you were doing this algebraically, what would that look like? Well, let's see here. I'd have cloud divided by 2 minus 3,000. Dividing this whole thing by 2 is the same as multiplying by 1/2. Taking half of that becomes cloud over 4 minus 1,500 with the distributive property equals 7,000. And then we can add 1,500 to both sides. And that gives me cloud over 4 equals 8,500. Then I multiply by 4 and cloud equals 34,000. Guess what? We get the same result. Okay. So many different ways to approach this. Totally up to you. I just showed writing an equation. Yes, you could guess and check. It is not a great strategy if you want to be perfectly honest. If there are not many things to guess, if you know the answer is either a 5 or a 7, go ahead, right? But if you don't have that as a context, you could be there for a very long time. Okay, another school book page, another school book page. What is this one? Grade 8. We got grade 6. Those are definitely equation ones. And we get into the homework. So my next video will talk about the homework. And I hope that that helps. If you have questions on the homework, you can let me know. I can meet you in Zoom. I can meet you on campus. I can record a video for you. Let me know how I can support you. I definitely want you to succeed this term. All right, let's make it happen. Off you go.